Um, so today is the second lecture on verification, and so recall on Tuesday we talked about reachability analysis and model checking. Those are topics that apply to analysis of any kind of system, not just embedded systems, but even commodity software. But today's lecture is on an analysis topic which is quite specific to embedded systems. I mean, it applies to other systems as well, but it's more important for embedded systems. And that's the topic of quantitative analysis. Okay, so I'll give you some examples of what quantitative analysis means. For safety critical embedded systems, like the systems that are in cars or planes or medical devices, they always, since they interact with physical artifacts, like you have a software in the car that controls fuel injection or the engine and so forth, you always have real-time constraints. So you might want to answer a question like this. Suppose you have a software task that controls the brakes in your car. Will the brakes be actuated in time for the car to stop? Right? So you might ask a question like, does the brake-by-wire software task always actuate the brakes within 1 millisecond? Okay. Now here the quantity is real time. But the quantity can be anything. It can be any resource that's being consumed by your system. So for example, if you write a new app and for the iPhone or some other consumer device, you might have a question about whether this will drain your battery within a certain amount of time. Okay? So that's another type of question which is specific to resource-constrained embedded systems and not so much other systems. And then finally, you have similar questions also for sensor networks and tiny sensor nodes that are used in a range of systems today. This is a device that's been proposed to be used in some medical devices to do encryption of data that's wirelessly transmitted. And because it's implanted in a medical device, obviously you don't want the encryption is a secondary task. The primary task of the medical device is to do whatever it's supposed to do, like the pacemaker, right? The primary task is pacing. The secondary task is encryption. And so they want to make sure that the secondary task doesn't really consume battery power, consume energy, right? And so the proposal was, let's use energy harvesting to do the encryption. But obviously you need to know how much energy you need to harvest in order to do the encryption correctly. So these are all questions which are quantitative analysis questions. They're all questions asking, will the program running on this particular platform consume a certain quantity, physical quantity, whether it be time or energy. So I think you might have seen this video earlier on the course, but I'll play it again because it's quite relevant to today's topic. So here you have this car on a factory floor that's being manipulated by 3 giant robotic arms. And one of the things you'll notice is that the movement by these 3 arms has to be synchronized in time. Otherwise, bad things will happen to this car, right? And actually, it turns out that these 3 this is actually a distributed embedded system. These 3 robotic arms are networked, and they are time synchronized over the network. And there's software controlling each of these arms. So you have real-time constraints, firstly on the network that's connecting them, and secondly on the code that's running in each of these arms. Okay? So that's an example, again, of a time-critical embedded system. Okay? So many physical quantities are relevant for the correctness of embedded systems or cyber-physical systems, but time is one of them which really stands out. So that's going to be the focus of today's lecture. But a lot of the ideas we talk about today will also apply to things like estimating energy consumption of a program running on a given platform. Okay, so there are several timing analysis or timing verification questions that arise in practice. Perhaps the most common one is something called worst case execution time estimation, WCET. This is a classic problem that people have been working on for 25 years, and it's still, you don't have a good solution. So it's one of these research problems that remains open. Now, if you go to talk to people in industry, they certainly are interested in WCET estimation, but they're also interested in a range of other things. So, for example, if you're not coding up a hard real-time system, but you have a soft real-time application like video streaming or some sort of audio-video decoding, then you may not be interested in the worst case, but what you'd be interested in is, most of the time, or on average, how much time does my decoder take, right? And here, the general question here is, you don't want just the worst case, but you want to be able to estimate the distribution of execution times that a program can exhibit, okay? Or you might have this question about, it's all very well to say that the program will take at most 1 millisecond in the worst case, but can you actually show me a test case that will make the program take that long? Okay, so that's the threshold property. Can you produce a test case that causes the program to violate its deadline? And then a lot of people who build real systems, you might have heard of hardware-in-the-loop simulation, where when they've written the code, they run it on the actual platform and simulated it along with either a model or with the actual artifact. But increasingly, hardware-in-the-loop simulation is too late to make sure that the system works correctly. So people do what is called software-in-the-loop simulation. And here they're simulating a continuous time model of the continuous part of your system. So typically this could be a Simulink state flow model or a LabVIEW simulation or something like that of the continuous part of your system. And then they run the code for the controller alongside in parallel. So they're basically running both the code, let's say the engine control software, and then they simulate the engine itself. And they do this in lockstep. And the simulation has to be synchronized in time, and they need to, for that purpose, they need to be able to predict how long a program will take along a given input, along a given path. Okay, so these are a range of timing analysis problems out there, and all of these involve predicting execution time properties of software. Okay, actually, earlier on the course, we ourselves came across this problem of execution time analysis when we talked about interrupts, right? Remember, we had this task where we had the main function and the ISR, and we were trying to figure out what happens if the main function gets interrupted at various points. And one of the assumptions that we had to make in order to convince ourselves that the code will work correctly is that a certain part of the main function will take a small amount of time, or the ISR code takes much smaller than the main function, right? So we had to make these timing assumptions. Today's lecture is about techniques to solve that problem. How do you figure out how long pieces of code will take? Okay, so most of the stuff I'll talk about today is in chapter 15, but this is really a current research topic. So there are people working on this problem all over the world. My group is also focused on this problem, but there's a lot of other groups doing nice work. So I've put in a bunch of references for you to go and read if you're interested. Okay, but the primary reference for the course will be chapter 15. Okay, so we'll focus on one problem, which is worst case execution time analysis. What is worst case execution time? Well, if you have a program, you have a software task, the time the program takes depends on the inputs you provide to that program, obviously, right? What else does it depend on? Yeah, Rafael? Yep, so it depends on the software environment. Other threads are running, the OS scheduling policy, interrupts. Right? The hardware target, absolutely, right? You run the program, if you run it on different processors, you'd expect to see different execution times that depend not only on the clock speed, but also on the specific characteristics of the processor. So the details of the pipeline, the details of the cache, the hierarchy, memory hierarchy, okay? So there's a whole bunch of things in the platform that it depends on. And all of you have programmed embedded systems that talk to the network as well, right? And so network delays will also affect execution time. So there's a whole bunch of things that affect execution time, right? And so I've said it's a function of input data, and environment conditions is basically a catch-all phrase for everything you mentioned, right? It's software environment, hardware, characteristics of the hardware, characteristics of the network, and so forth. Sometimes we're also interested in the best case execution time. So this is the longest time it'll take. The best case execution time is the shortest time the task will take. The reason people want to find out best case execution time is sometimes they're interested in finding an interval in which the execution time lies. So if you know what the BCET is and the WCET is, you know that the time the program takes on any input on any under any state of the platform will lie in that interval. Okay, and then you can use that in scheduling algorithms, for example. So here's a picture which illustrates, all the different quantities related to execution time that one might be interested in. So let me explain what this plot is first of all. The x-axis is time, and the y-axis is the frequency with which the program exhibits a particular cycle count. So x-axis is, you can think of it as CPU cycles, and y-axis basically, let's say if this bar is 100, it means there are 100 inputs and states for which the program exhibits this time. Okay, so it's basically the empirical distribution of execution times. And let's say the darker curve, the one on the top, that's the true distribution, right? And so the true worst case execution time is this x value, and the true best case execution time is this x value. Okay. But when you actually test the program, when you just test it on a bunch of inputs and on a bunch of different platform states, chances are if you don't do your testing correctly, you won't see the worst case or the best case. You won't see the extreme cases. You'll see some average case. So that's what the lightly shaded curve is. So this point on the x-axis is the minimum time that you observed in your testing. And this point on the x-axis is the maximum time you observed in testing. And clearly, this is less than WCET, and the minimum time is bigger than the BCET. Okay. Now, there's a whole bunch of industrial tools out there that try to find this, but they really can't find it very precisely. So instead, they try to find an upper bound on the worst case execution time and a lower bound on the best case execution time, which means they're basically trying to increase this interval. So they find something which is a little bit bigger. Hopefully for their purpose it will be conservative, right? If all you want is a bound on your worst case performance, then finding an upper bound is good enough. Of course you care about how good it is in practice. Okay? So here's the statement of the WCET problem. You're given the code, the program that you're interested in, and then you're given the platform. So let's say you're given the actual hardware. Let's say, just to make things simple, let's say it runs bare metal, so there's no OS to deal with, and there's interrupts, but let's say there's no threads, right? So you're just given the platform that will run on, and the question is determine the WCET of this task. So one of the reasons I talked about already, which is why this problem is important, is for safety critical embedded systems, right? You're interested in, will this task finish in a given amount of time? And so if you can find the worst case execution time, and that's less than your bound, like 1 millisecond, then this program will always finish within 1 millisecond, right? So that's one reason why it's important. What's another situation in which you can use WCET values, which you've already seen in this course? Yeah? Scheduling, right? So in the scheduling chapter, typically in a scheduling problem, the setup is you're given n tasks, and then each task takes so much time, right? And in the scheduling chapter, we basically assumed that we knew the times, but you have to figure them out somehow, and finding WCET is one way of figuring it out. Okay, so if I just state the problem like this, right, and I say, okay, can you come up with an algorithm that will find WCET always for any program? Is that possible? Nope. Why not?
Because you can't take into account things like
okay.
how you take into account, guys pressing a buzzer, time a second, or like something.
Okay, so let's leave out interrupts for the time being. Let's say there's the program you're only interested in running a part of the code which you know will run uninterrupted. So I've simplified the problem a little bit for you. Yeah.
Maybe stuff we talked about last lecture, like if there's a while loop that depends on if it gets a certain.
Okay, that's so you don't know if it will get to that point. Is that how long it will take? Well, that's the problem, right? Yeah, but I think you're close because you talked about while loops. So
Maybe you might not always have something that be accessed.
I'm sorry, I can't hear.
Might be accessed in memory.
Might be accessed in memory. Why would that make this problem hard?
Or just because, I guess for the worst case, you could always assume that.
Oh, I see. You mean like okay, you have a cache miss and you have to go to main memory. Yeah, so maybe for the worst case, you can always assume that you have cache misses, although it's a little trickier than that, and we'll see later. But let's say, okay, you don't even have any caches. Make it simple. You just have like a single memory. You have a main memory. You go to main memory each time you have to do a memory access. So it's a fixed amount of cycles each time. Yeah.
I think if you're not connected to the outside,
Yeah.
so if you're disconnected from outside world, yes, we could. So
Yeah.
if you disconnect every bounds to outside world, we could measure the time.
Uh-huh.
If you have any connection to outside world, other than the computer world,
Yeah.
probably we can. So we need to actually, like, we could measure.
Uh-huh.
Yeah, actually measure.
Okay, so the question is not about, you can measure the time, you're right. But the question is, can you determine the worst case, right? So measuring is along one input. For the worst case, you have to do measurements along all possible input sequences you can ever get, right? So, yeah, Karthik? Okay, you have to account for recursion, right? One more. Halting problem, right. Okay, so that's it, right? So you have to solve the halting problem to figure out the worst case execution time. Given any program, right, you have loops, you have recursion, you can very easily write programs that don't terminate, right? So that's the fundamental challenge. The WCET can't always be found unless you make assumptions on the kind of program that you're working with, right? If you have arbitrary programs with arbitrary loops and recursive function calls, then the problem is undecidable. Because you can, I mean, we all typically program in Turing complete languages, languages that can encode Turing machines, right? And so you can very easily encode an instance of a program that doesn't terminate, and then the WCET task will have to solve the halting problem. So that's the fundamental problem for WCET. Although I know I can see that a lot of you are really embedded systems people because you make the right assumptions about programs already, right? So it took a while to get to the halting problem here. And so the thing is that in embedded systems, you don't write the parts of the code that you're interested in putting real-time bounds are usually very carefully written so that they do terminate, in the sense that you write loops where you know the bound on the number of iterations the loop will take. And if you use recursion, typically recursion is disallowed, but if you do use recursion, then you have to think about what the recursion depth is, how many times the function is going to recurse. Okay, so there's actually a very nice article by Gerard Holzman, who's at NASA JPL. He has this, I think it was in CACM, or maybe IEEE computer, I don't remember, a few years ago. So, Gerard Holzman, and he has this rule of 10. So he has 10 rules to follow when you're coding embedded systems software. And one of those rules is that make sure all your loops have statically known bounds. You know the bound before you compile, right? I mean, I think this has got a lot of traction within NASA, for example, in just implementing their systems. So if you think about what your Cal Climber was doing, it's actually something like this. You have an infinite loop. This is a good time to turn up the volume, I guess. So you have an infinite loop where the Cal Climber is constantly looping around, And then at the start of the loop, it reads the sensors, right? So it reads from the serial port to see what the state of the iRobot sensors are, and then it reads from the ADC to see what the state of the accelerometer is. And then based on that, you do some computation. So you figure out, oh, I have to rotate by so much, or I have to drive forward so much, etc., or I have to reverse. And that's the compute part. And then you actually write the command to the actuators. So you write, again, to the serial port, and you say, for each wheel, you say, drive with so-and-so velocity, right? So that's the typical form of an embedded system. And typically what we're interested in for timing analysis is just finding out how long this part takes. And this part typically is written very carefully. You have loops with finite bounds and no recursion, so there is no halting problem to deal with. You know the problem, this program will terminate. And typically, there are some assumptions that tools make. So if you ever need to use an industry tool in the near future, chances are that they'll assume that the code runs uninterrupted. This is not a good assumption, right? Because typical embedded systems code does use interrupts. However, the reason the industry tools don't use it don't actually handle this case is because it's a hard problem. It's still an unsolved problem. So this area still has a lot of problems that remain to be solved. And then they also make assumptions that this part of the code runs single-threaded, which is usually reasonable because you're only interested in timing the single-threaded parts, and then you have something else, which a different kind of analysis, which then finds a bound on the overall multi-threaded system. Okay, so this is the setting we're going to use. We'll be interested in timing programs with finite bounds, no recursion, and which are single-threaded, and we assume no interrupts. Okay, so I'm going to talk about this in 4 stages. Hopefully, we'll get through all of it today. The first is just a view of programs as graphs. Those of you who've taken 164, you'll find this familiar. But it's just so I get everybody on the same page. We'll talk about what a control flow graph is very briefly. And then we'll talk about what are the problems you need to think about when you do execution time analysis. Okay, so we'll go through a set of examples for this. Then I'll talk a little bit about how current approaches work. And I'll talk about how you should measure execution time on a platform. Even measuring execution time just for one input is not trivial. And so we'll talk a little bit about that. And since this is a current research topic, I'll talk a little bit about future directions. Okay, so here's a simple program drawn from the textbook. This program does modular exponentiation. Okay, so modular exponentiation is a common subroutine in cryptography. So this function takes in 3 inputs: the base, the exponent, and the mod. And what it computes is base raised to exponent, okay, and mod this quantity, okay. So it's computing this value, but it's doing it iteratively. So you have this while loop, which the intention is it makes one iteration for every bit of the exponent, right? So your exponent could be some number, right? And what you're doing is you're testing the bits of the exponent from least significant bit to most significant bit, okay? So if let's say this is the first iteration, if the LSB is a 1, then you multiply the current result. So in that case, you'll just be base mod this quantity and store it back in result, right? So if in any iteration the corresponding bit is a 1, you'll simply multiply base into the current result and store it back. And then you shift the exponent right 1 bit, you square the base and iterate, okay? So that's what this program is doing. So here I've defined the number of bits of the exponent to be 32, right? So we're going to think about these programs as graphs, In particular, we'll use the control flow graph representation. So in the control flow graph representation, the nodes of the graph correspond to what's called a basic block of the program. How many of you have heard what a basic block is before? Okay, just one. So a basic block is essentially a straight line piece of code where the entry point is only at the top and the exit point is at the bottom. Okay, so let's go back and look at this function here. So if I look at this first part, right? So here you have an assignment. You set result to 1, and you set I to x bits. Now this is a straight line piece of code. You know, after executing this, it's going to come to this statement. It's not going to exit anywhere else, right? And remember again, the code is running uninterrupted. But now at this point, at the while loop, if I were to, if I took my program fragment to be, let's say, the first 4 lines, so lines 7, 9, 10, and 11, then I no longer have a basic block because at line 10, you either go sequentially to line 11 or you might pop out of the loop, right? So line 10 cannot be in the middle of a basic block, right? And typically when you have conditionals, you put them that you could either put them with the previous basic block or you could make it a separate basic block as we have done here. Okay, so what we've done here in this program is we have taken out every straight line fragment which is entered at the top and exited at the bottom, and we have put it into a separate node. Okay, so you have 6 such basic blocks in this program. And then the edges are simply the flow of control. So this edge is added because after executing this assignment statement, you go to the while loop and you test this conditional, right? And so there's a flow of control from the end of this assignment to the beginning of this statement. Okay, and similarly, this is a conditional. So there's 2 possible branches you can make. If this conditional is true, which is represented by the 1 on the arrow, then if I is greater than 0, you go and you test the next conditional, which is this if statement, right? But if I is less than or equal to 0, then you take this edge and you'll exit the while loop and execute the return statement down here. Okay, so each of these edges model control flow of control from the end of one basic block to the beginning of the next basic block. And for conditionals, we label it with 1 and 0 to indicate the value of the conditional. But if you have unconditional jumps, then there's no need to indicate a Boolean value with the edge. Okay, so that's basically what a control flow graph is. So now the problem is instead of thinking about programs, let's think about control flow graphs. And you have a starting node in the graph and you have an ending node in the graph. So a source node and a sink node. You might have loops, but you should have a bound on how many times you go around the loop. And now the problem becomes, in some sense, a graph problem, right? You want to find the worst case execution time of this program. That corresponds to finding the longest path in this graph from the source node, which is the node number 1, to the sink node number 6. Okay? Questions about this? All right, so if you look into the guts of any execution time analysis tool, there'll be 2 components to it. The first is doing something called program path analysis. So remember that the goal is you have a graph like this and you want to find the longest path from the source node to the sink node. Now, at a high level, this is just a graph problem. But if you look a little closer, it's a very special kind of graph. Okay, the first thing is that not all paths in this graph from source to sink can be executed. Okay, so we'll look at examples where there exist paths if just in the graph, but the conditionals are such that if you take this conditional, if that's true, then the other conditional has to also be true, right? And you can very easily come up with examples like that. So a path that you can actually execute in the program is called a feasible path. Okay, So we have to identify feasible paths. We have to find loop bounds also. Sometimes the loop bounds are obvious. Sometimes they're not so obvious. So if people don't follow things like the rule of 10, then sometimes it takes a little effort to find a loop bound, even though the program may terminate, but you have to think a little bit to convince yourself. And then the other thing is there are often dependencies among different code fragments. So we'll talk about that also. The second aspect is, as you all pointed out earlier, the timing of a program depends on the platform, the hardware and software environment. And so you need to be able to model all the details of the platform. This is called processor behavior analysis. Okay. So let's look at the program path analysis first. And all of these examples are in the textbook. Okay. But I'm just using them to illustrate different problems that the tools have to consider. So the first problem is path explosion, right? So even if you write you can write very small programs which have just a humongous number of paths. Okay, so here's a program with a nested loop. So you have two for loops. Okay, each of these loops is executed 100 times. So max size is 100. Okay, so this for loop is executed 100 times. This for loop is executed 100 times. And then in the middle of the for loop, you have this conditional. Okay, so this conditional is saying if the array value is non-negative, then you increment the positive count and you accumulate the value into the positive total. Else you accumulate the value into the negative total, right? So if you're thinking about this as a graph, then how many paths do you have from the top of the for loop to the bottom of the for loop? Karthik? Is it max size square? Okay, so the number of iterations is max size square. The number of iterations of the for loop is max size square. So you execute this. You execute this statement 10,000 times. Max size is 100. It's 10,000, right? But 10,000 times you have to execute something that looks like this. Right? You have a conditional. If it's 1, you go this way. If it's 0, you go this way. And then you have a loop around this which goes 10,000 times. Right? So the total number of paths is 2 raised to that. Right? Because the number of choices you have, each time you make an iteration, you have a choice of either going left or right. Okay? And the total number of choices is the total number of paths, which is 2 raised to 10,000. Right? So even a program like this, very innocuous looking, has an exponential number of paths, right? And this is actually fairly common, right? It's common to write a pattern where you go around a for loop and based on some conditional you do different things. So so this is one problem that you have to deal with, right? So if you're finding longest path, if it wasn't a program, of course, longest path algorithms for graphs like this, which can be unrolled into DAGs, that you can do that in polynomial time. But this is a program, so it's a little bit more complicated than that. Okay, the second problem is just finding loop bounds. So here's the module exponentiation program we saw earlier, and I want you to just focus on this loop going from 10 to 17, right? Now, the intention is that this loop, the number of iterations of this loop is equal to the number of bits of the exponent, right? So in this case, the exponent is of 32 bits. Therefore, we want this loop to execute 32 times, right? But how would you convince somebody that this, in fact, executes 32 times? What's the proof argument you'd use? It may seem obvious, but I'm just looking for, what's the one sentence proof that you would give to someone to show that this terminates in 32 cycles, 32 iterations, sorry.
Because we start from 30 to subtract 1.
Yeah, exactly. right? So the key point is that you start at a finite number, 32, and you decrement that counter once for every iteration, right? And then the final thing is that the conditional, the loop terminates when the counter hits 0. Okay. Now in this case, it's actually easy to see that the loop terminates because the loop counter is the same as the program variable of interest here. But in other examples, you have to make up a loop counter. Basically, you have the way you convince yourself that a loop terminates is you say there's some imaginary variable which could be a function of the other variables in your program, which gets decremented once every time. So it starts at some finite value and it gets decremented and it goes to 0. And so that's the way people prove termination of programs. Okay, manually they have an invariant which says, each time I go around the loop, the value of the counter is less than the previous value of the counter. Again, for embedded code, the goal is that since you can't really prove program termination in general, you have to follow rules, fairly strict rules. And in this case, the rule we're following is that the loop counter gets decremented once every iteration, for sure, because any path through this loop has to decrement I. Okay, so if you make sure that you have that kind of pattern in your code, then this loop will terminate. Okay, here's another issue. So I told you that not all paths in a program are feasible. Okay, so here's a very simple program, a very simple software task, which is actually drawn from the controller for a UAV. So if you look at this code, it's let's just see what it's doing. It's computing. So the goal of this code is to set a particular climb parameter for the UAV. And so first, what it does is there's a desired altitude it has to get to. It has an estimate of its current altitude. So it finds the error, and then it computes how much it has to climb, how many meters it has to climb, based on the value of that error. And then this is a floating point quantity, right? So one of the things you have to be very careful of in embedded software is overflow and underflow, right? So what they do to avoid it is they use something called saturation arithmetic. So basically, saturation arithmetic, the idea is that if the value of this variable becomes too small, and too small is defined by the value of desired climb is less than minus climb max, then it saturates at that value. Okay, so you never allow a variable to become too small, and similarly, you never allow it to become too big. So if desired climb is greater than climb max, then it saturates at climb max. Okay, so that's the program. How many paths does it have from beginning to end? 4, right? So you have 2 conditionals, and each conditional can go either way, right? So you have 4 possibilities. Of these 4 paths, are all 4 paths feasible? Can you execute all 4 paths? Unless climb max is negative. That was a sort of a trick question. So it really depends on the value of climb max, right? Actually, it turns out here for this program that climb max is 1. It's a positive quantity. So what happens is, let's say if climb max was, what happens is that you can only execute one of these 2 assignments. Okay, so just to convince yourself of that, assume that both of these conditionals become true. This means that climb max was initially less than minus 1. So you set it to minus 1, which means it cannot be greater than 1. Okay, and so basically it means that this assignment cannot be executed. All right. So if climb max is any number which is non-negative, then you will only execute one of these 2 assignment statements, which means one of the 4 paths is actually infeasible. You cannot execute it. The remaining 3 paths are all feasible. Okay, but if climb max is negative, then in fact you have 4 feasible paths. Okay. So this is another thing you need to figure out. And doing this for the little program is, this was easy. We could do it by hand, right? But doing it for a more complex program is, even if the program terminates, is an NP complete problem. So you need to be able to solve the Boolean satisfiability problem to be able to figure out if a path is feasible or not. Fortunately today, the SAT problem, even though it's hard in theory, you can solve it in practice. And if you're interested in that, there's a very nice CACM 2009 article by Malik et al. So you can, it's a very accessible article about SAT solvers. Okay. So the other thing you have to think about is not just the program path analysis, but also how characteristics of the platform can affect the execution time of your program. So here's a little example of that, dealing with cache effects. Right? It's kind of things that was pointed out earlier. So here's a program that computes the dot product of two vectors. So you have one array x, which represents one vector, and then you have an array y, which represents another vector, and n is the dimension of the space. So n is the size of x and y. Okay? And so what you do here is the obvious thing. You have an iterator I, and I goes from 0 to n minus 1, and you simply take xi times yi and accumulate that. Okay, so now let's think about what happens for this code for different values of n. Okay, and let's assume that this is running on a 32-bit processor. So what that means is that a float is 32 bits. Okay, and also so each time you access x of I and y of I, you're making an access to memory, but you have a cache, and the cache is direct mapped. Right? So anybody remember what direct map caches are? Yeah, Dosa? Okay. So a cache is made up of sets. You're almost right. Each set has a single cache line. Right? That's what a direct map cache is. So here the cache has two sets. Right? So this is your cache. That's set number 1, and this is set number 2. Let's call it 0 and S1. And you can store 4 floats per set. Okay. And furthermore, if you the other assumption is that in memory, x and y are stored contiguously. So you first have x0, etc., to xn minus 1, and then you have y0 to yn minus 1. Okay. So x and y are stored contiguously, starting at address 0. Okay. So now let's think about what happens when n is equal to 2. So when n is equal to 2, you have x0, x1, y0, y1. And remember, you can have 4 floats here and 4 here. Right? So when you run this loop, you'll read x0, then you'll read y0, you'll compute the product. Then you read x1, read y1, and you'll compute the product, and then you're done. Okay? Let's assume that result is sitting in a register, so it has nothing to do with the cache. All right. So how many cache misses do you have, and how many cache hits do you have? Yeah, Apurva? Okay. You have 1 cache miss, correct. So if n is equal to 2, you have 1 cache miss because all of these will end up in the same block, right? x0, x1, y0, y1, and they'll all end up in the same set. So now you'll have a cache miss for x0, but then you'll read in the cache line into the set, and then you would have hits in all of these three. Okay, so when n is equal to 2, then you have 1 miss and 3 hits. Okay, what happens if n is equal to 8? So remember what's happening is you'll have x0 to x7, and then y0 to y7. Sorry? 4 misses. How would that happen?
First time you pull out x0 to x2 and
Okay. Yeah, so you'll have x0 to x3. Yeah.
And then 1 plus 1 less.
Yeah.
Y0 to Y3.
So let's just see the pattern of accesses. So you'll pull in x0 to x3 here, right? And so x0 to x3 will map to set 0. x4 to x7 will map to set 1. y0 to y3 will map back to set 0. Okay? So basically, both x0 to x3 and y0 to y3 will map to the set, and x4 to x7 and y4 to y7 will map to this set. Okay, so you have a miss on x0, right? But then what's the next thing you access after x0? y0, right? So you have a miss here, then you have a cache miss here, and then x1 again. So you basically have a cache miss on x1, evict all of this, and then you have a cache miss on y1, right? So it's going to end up with you have cache misses for every single access, right? This is a pathological bad case, right? But it can happen. So a seemingly very simple change. It wasn't even a change in the code. It was just a change in the value of a parameter to this function, right? That's it. And that changes that has an impact on how long this program will take. Okay. So these are the kinds of effects you have to think about. So if somebody asks you, well, how long does this code take in the worst case? Well, it actually depends on a number of things. It all depends on all the program path characteristics we talked about, right? You have to think about which paths are possible, which are the longest paths among them, and then you have to think about the values of variables. Okay, and how they impact on the platform. Okay, so how do things work currently in practice? If you take the state-of-the-art tools, this is what they do. State-of-the-art industry tools. They have engineers who pore through pages and pages of documentation on processors, and they manually construct a processor behavior model. Basically, this is they model the cache and they model the pipeline and they model everything very carefully, and then at every basic block, an engineer thinks about, well, what happens if I execute this basic block? What happens to the cache? What happens to the pipeline state? What happens to the branch prediction unit? All of that. So you have to think about all of these things. Clearly, you can see that for sort of modern processors, this is impossible to do manually, right? And in fact, I've heard stories where people have basically gone to a company and said, I have this slightly customized version of a processor you already support. Can you extend your tool to deal with my processor also? And the company comes back and says, I'm sorry, it will take us about a year to do that, right? Because it's actually a very human-intensive task, right? Engineers have to look at this, and they have to come up with an accurate processor model. But anyway, that's how it's done. So you can manually construct a processor behavior model. Then you use that model to find the worst case starting processor state for every basic block. So for every basic block in the program, you think about what is the worst case state. And this is not manual. It's mostly automatic how they do this. And then once they found the worst case, they measure the execution times of the blocks from these states. So which means they initialize the platform in that state, they run the code and see how long it takes. Okay? So we'll talk a little bit about what's required to accurately measure execution time, but this is also a non-trivial task. Okay, so now once you've done that, basically at the end of this second step, you have the worst case execution time for every basic block in your program. Okay, so you've solved the problem for little pieces of code, little straight line pieces of code in the program. So now you have to pull those together to find the worst case time for the entire program. And so you use the times you get at the end of step 2 as upper bounds on the time of every basic block. Well, this is the worst case time, and so this is an upper bound on the time of that basic block. And then you formulate what's called an integer linear program. How many of you know what a linear program is? A few. So we'll see an example of that also. It's a particular kind of optimization problem. And you solve that optimization problem, and that tells you what is the maximum sum of the bounds on execution times that you can have along any program path from source to sink. Okay? And the solution of this integer linear program is the value we're looking for, which is the upper bound on the worst case execution time. Okay? So this approach really only solves one of the problems we saw at the beginning of class. It only finds a bound on the WCET, worst case execution time, which is quite useful in practice for scheduling and other tasks, but it doesn't solve all the problems that people are interested in. Okay, so let's take a look at how this part is done. So we really can't talk about this manual processor model construction step because even talking about it is really tedious. Well, actually, I personally believe this is not the right way to go. So I'll have more to say about that at the end of class. This part we'll talk a little bit about later. What I'm going to focus on is steps 3 and 4. Okay, so here's a little toy program. So this is the program you have here. You set n to 10, q to 0, and then you have a while loop, right, which loops around as long as q is less than n. Q starts off at 0, and you increment it each time. So you can convince yourself that this is terminate in 10 iterations, right? And then you exit after 10 iterations, and then set q to r. So the control flow graph looks like this. So now the first thing we'll do is we'll introduce variables to stand for the number of times each node and each edge is executed in the program. So let d1 be the number of times you enter basic block b1, and d2 is the number of times you exit basic block b1. Now, of course, we can look at this program and say d1 is going to be 1 and d2 is going to be 1, right? Now, if you look at basic block b2, it's not going to be just 1, right? It's not trivial. So b2 is entered how many times? 11 times, right? That's going to be d2 plus d4. And it's exited d5 plus the d3 times, which has to be equal to the number of times you entered it, right? Okay. So you're getting the hang of it. So these are the number of times you take every edge, and the xi's are the number of times you execute the code inside the node. Okay, that has to be the same as the number of times you entered it. Okay. So now what we'll do is we'll write constraints, equalities that relate these different variables. Okay. So xi is the number of times basic block bi is executed. And dj is the number of times the jth edge is executed. So then we'll have these constraints. So we say x1 is equal to d1 is equal to d2. And that's one constraint. And then you have d1 is equal to 1. You enter the program just once. x2, the number of times you execute this while conditional, is equal to d2 plus d4, which is equal to d5 plus d3. That's that constraint. And then x3, which is the body of the loop, right? The number of times you execute the increment operation. That's x3. So that we discussed was 10, because the number of times you execute the loop is 10 times. So x3 is equal to 10, which is equal to the number of times you enter b3 equal to number of times you exit b3. So x3 equals d3 equals d4 equals 10. And then x4 is equal to d5 equal to d6, right? So this is the set of constraints you will write down, and let Ci be the upper bound on basic block Bi. Okay, then what you want to do is you want to maximize sigma over all I Ci times Xi, right? So this is the number of times you execute basic block I times an upper bound on how long it takes each time you execute it. Okay, so the Ci times Xi is going to become the upper bound on the total time you spend running basic block I. You sum that for all basic blocks, and that gives you the total execution time. Okay, so this optimization problem is an integer linear program. It's a linear program because all of these terms are linear terms. They only involve addition or multiplication by a constant. Okay, and it's integer because xi and di are integer values. Okay, so they're variables that take integer values. All right. Any questions about this? So this is at the guts of all tools, industrial tools that do this execution time analysis. Okay. Now, timing analysis is a tricky problem. One of the reasons it's a tricky problem is it's not compositional. So, compositional analysis means that if I have a program which has two parts A and B, so T is A semicolon B. So this is a program A, and then after finishing A, you run B. Then what you would like is that the worst case time of T should be simply the sum of the worst cases of A and B, right? This is the obvious thing. You would expect something like this to be the case, right? And if it was the case, then it makes your life easier because you can find the worst case of this block and then the worst case of that block and be done with it, right? You can break if you have a large program, you break it into small pieces, you do the worst case analysis on each one, and you add them all up. Okay, but the tricky bit is this is not always the case. Okay, because there can be dependencies between A and B. The execution times of A and B can have hidden dependencies through the hardware platform. So here's it leads to a different kind of timing anomaly. We saw some timing anomalies where we talked about scheduling. Basically, a timing anomaly is a situation where you expect one thing to happen, but the actual worst case is something else, right? And so you might expect that that if for a program that accesses the cache, the worst case might always be when there's a cache miss, right? But there's a situation reported in a bunch of papers where actually getting a cache hit is the worst case, and here's how it happens. So let's say A is a piece of code, a basic block you execute in going from this point to this point, and then there's a conditional, and then B gets executed. Okay, so what happened in this scenario is that if you have a miss, let's say, so this is a miss in the instruction cache. So you're trying to get the instructions, fetch the instructions for A, you miss in the instruction cache. Therefore, the time to execute A is long because you have to first get the instructions from main memory and then execute them. Okay, so you execute A, and then at some point after you execute A, the branch target is evaluated, and then you're ready to execute B. Okay, so that's the miss case. You'd expect the hit case to be easier. So here the instructions in A are in the cache, so it takes a shorter time to execute. But what happens in this process is that it could be the case that the processor is in a state where it's speculating. So it starts to speculate that, even when it's executing A, it starts to speculate that it's going to take this branch, right? And so it starts prefetching the instructions along this branch, which evict the instructions of B, which were already in the cache. So it prefetches, and then at some point you evaluate the branch and you find, oops, you don't have to. The branch doesn't go this way; it goes the other way. So then the pipeline has to stall. You have to bubble out the instructions that you fetched, started executing along this path. So that takes a little bit of time, and then you start executing B. But now executing B takes a longer time because the instructions are no longer in the instruction cache. Okay, so this is a real situation that was observed on an embedded processor, where they thought, oh, to get the worst case time of A and B, I'll just take the sum of the worst case of A and the worst case of B, and that will be the biggest value. But they didn't account for the fact that you can have the speculative execution going on in the processor, which can incur a penalty, and you have to also add the little bit of the small number of cycles that corresponds to dealing with that misprediction. Okay, so yeah, Nima.
Why don't we do the prefetch for the second thing that we didn't guess?
Because in this case, I think. So I think the branch target was evaluated in time, but it could just be that the state of the branch predictor was such that you didn't predict the same way as you did in this case. Yeah. That's right. Yeah. So I guess the instruction would be fetched here, and then the question. I think Nima's question is, why isn't it being prefetched here? I think it's a fair question. I don't know all the details of the situation, but it didn't happen. Yeah. Yeah, so I think the difference is really in the timing. When did you execute the instructions? So in this case, when you had a cache hit, you would have started executing instructions in A earlier, and then you would have in the pipeline. You would have hit you would have speculatively started executing instructions. And then the branch target is not yet computed, and so you would have to. It could be the branch prediction unit just decided to predict that the branch goes one way than the other in this case, and in this case it was the other way around. I can look up the paper that reports this in more detail and find out exactly what happened here.
Doesn't that seem like the prefetch stage was?
The prefetch stage was the problem, exactly. Yeah, that's the point. The prefetch stage did not happen here, and it happened here. But I think that the issue that is being brought out here is that if you just focus on one part of the processor and you say an instruction cache, the miss is this problem and the hit is not the miss is always the worst case, right? Let me just do this part analysis based on the instruction cache miss state at this point, and optimistically assume that this will never lead to a worst case situation, then you would not find the worst case execution time. Okay, so that's, I think you have to consider the interaction of all the different architectural features in order to figure out what the worst case is. You can't just localize and say, okay, I'll just think about the worst case for the instruction cache, the worst case for the data cache, etc. in isolation. Okay. All right, so let's talk a little bit about how to measure runtime, because ultimately, whether you do this processor modeling and the approach that we talked about earlier, which is to find an upper bound on every basic block, or you just run tests and see how long the program takes, you need to be able to measure execution time. Okay, so how would you measure the execution time of a program on any processor? You must have done this, right? Yeah?
So you can reproduce something.
Yeah?
So you run the program and the program terminates, you can document the difference.
Right, okay. So you start a timer, you run the program, and you sample the timer at the end, right? That's basically how you do it. On a commodity OS, right, Windows, Linux, you typically have function calls, system calls that you make to sample the timer, right, before and after. But in embedded systems, you have to be careful if you're doing that, because when you make a system call to sample the timer, it actually it has two effects. One, you're changing the code because you're inserting those calls, and so just the code of your program changes, and so that changes the things like the instruction cache characteristics. The second is that even the function call to access the timer will take several hundreds of cycles if it's a function call, right? And so that adds an overhead. So the thing to do, ideally, if you can do this, not all platforms allow you to do this, is to try to directly sample the CPU cycle counter. Okay, so a lot of processors have cycle counters in them. So in order to for the architects to just use for performance tuning of the processor, right? And so you can try to sample these CPU cycle counters using inline assembly. So this avoids the overhead of making a system call to sample some operating system state. And so hopefully it has two effects. One is the amount of code you have to sample the cycle counter is just a few instructions. And secondly, the number of cycles that code takes to execute is also small, right? So it reduces the impact in both code as well as the amount of execution time. Sometimes you don't have the processor ready. So you're still developing the code and you're evaluating a bunch of different backend processors that you could use. And so at this point, if you don't have the hardware, the next best thing is to use a simulator for the hardware. The thing to remember is if you're interested in timing, you must use a cycle accurate simulator, which actually gives you the right CPU cycle count. But sometimes neither of these are good enough, and what people use are logic analyzers, where they basically, you don't actually modify your code, you just define events in your code, which are, basically the program counter reaches a given location, that's an event, and you have an off-chip analyzer that will get triggered each time the PC reaches a certain value, and you have a timer based on those events, which is recording the number of CPU cycles between events of interest. So this is more accurate, but obviously it's a much more complicated apparatus to measure. So let's talk a little bit about how you do things with cycle counters. And these are slightly old example, but I think you can still do these on Intel platforms. So on Intel platforms, you typically have something like an instruction which reads the cycle counter, so read timestamp instruction. And on 32-bit machines, this was a 64-bit counter. So the 64-bit counter wraps around only every 293 years. So seems good enough for embedded applications. So the way you do this is you would get the current value of the cycle counter, run your program, get the new value, and then subtract, right? And so the key thing is, how do you actually get the current value of the cycle counter? So if you're using GCC, then the thing to do is to write inline assembly. So you could do something like this, which is basically saying, so you have two locations here. These are two 32-bit locations storing the low order 32 bits and the high order 32 bits of the counter. And so what this is doing is it runs the read timestamp counter instruction. That instruction stores the low order bits in EAX and the high order bits in EDX. Okay, and so what you do here is this is a move instruction, which is moving the high order bits to the location you want it to be stored in, and the low order bits to the location you want it to be stored in, right? So basically you have three instructions doing the whole the sample of cycle counter. You have the read timestamp instruction, and you have two moves, and that's it. Okay. So now once you get this is actually the core code, and the rest of it is just wrappers around it. So this is you just wrap the ASM in a function, for example, access counter, and this will return the high order bits in this location and the low order bits there. And so once you've accessed the counter, it reads the values into the new counter high and the new cycle counter low. And and this is just doing the subtraction. So if the old values were in cycle low and cycle high, then this is the way you can compute it. The details of this slide are not that important because it has to do with 32 versus 64-bit. Okay, but if you have a 64-bit machine, then you could probably don't have to do this thing, and you can just do a single read and a single move, and you'll be done. Okay, so the high level, the problem will, your code will look like this. You'd start the counter, and starting the counter would be, reading the current value of the timestamp counter, and then you run your program, and then you execute get counter, which will again run this code and get the new value of the counter, and then take the difference, and that will be returned as T cycles. Okay, so to summarize, this is exactly the same as you would do it with a system call, except instead of a system call, you're using inline assembly, right? Okay, so looks straightforward enough. What are the things that can go wrong? So I want you to think about modern architectures. So what is the current hot topic in computer architecture? Multi-cores, right? Okay, so if you're running a task on a multi-core machine, and you are sampling the cycle counter on different cores, right? What do you have to think about? Which core are you running on, right? And does the task run on a single core, or might it be migrated to another core? Right? So that's one issue to think about. Okay. What else? How about for embedded platforms? There's often power management, right? So you have dynamic frequency and voltage scaling. So think about frequency scaling, right? So if that's happening while your task is running, then one cycle doesn't mean the same thing, right? So you might get a certain cycle count, but you can't translate it into a second or millisecond value in a straightforward way. You need to know what the frequency was when you were running it. Yeah. Yeah, so time taken by a function call can also affect how long this measurement takes, right? And so we implemented this as a function call. Of course, you don't have to implement it as a function call even if you want your code to look pretty, right? You can write it as a macro in C, and that way you avoid the overhead of having a function call. It's a good point. So there's actually a bunch of different things that can happen. So the instrumentation, as you pointed out, that incurs a small overhead. And typically, if the size of the program is much longer than the size of the 3 instructions that you inserted, then it's not a big deal. It's a little bit of noise, but you can account for that. Cache effects can skew measurements, but this is something we want to capture. We talked about multi-cores. We talked about power management. Multitasking is also an issue. So in this lecture, we assume that the code runs single-threaded. But if the code is actually not running single-threaded, then it's possible that you start the counter, you start running P, and then you get a timer interrupt. The OS scheduler decides to run some other thread, and then what that means is that the cycle counter is still ticking away. Even it's counting the number of cycles for the other task. Okay, so you have to make sure that you are measuring only the task of interest. Okay, so there's a sidebar in the book that talks about a bunch of WCT estimation tools, and there are some commercial tools. The one that my group is developing is called GameTime, and GameTime is based on a very radically different approach to the previous tools. So I'll give you a little view of what GameTime is all about, and we're always looking for students to work on the GameTime project. So if you're interested, come talk to me anytime in the next 1 month. So the way this works is you have a program, and we know how to do this. So from the program, you get the control flow graph, right? And if you unroll loops and you inline functions, the control flow graph becomes a DAG, a directed acyclic graph. Okay. So the next thing that GameTime does is it extracts a small set of paths from the program which are feasible. So these paths are paths that you can actually generate test cases to execute them. That's what feasible means. And moreover, they are a subset of paths that form a basis for the space of all paths. So this is in the standard linear algebra sense. You can think of every path as a point in a high-dimensional space, and we extract a subset of paths that forms a basis. And we use a kind of a SAT solver, which is known as an SMT solver for that. And then once you have a bunch of test cases and you have the program, you compile the program, and then you actually run the program on this set of test cases. Okay, so this is a carefully chosen set of test cases that you run the program on, and you measure how long the program takes on every test case. So if, let's say on input 1, I1, it takes 42 cycles, and input I2, it takes 75 cycles, etc. And what we do instead of having somebody manually model the processor, we have a machine learning algorithm that automatically generates a model from these measurements. So really the goal of GameTime is to get rid of the tedium of generating these processor models manually by exploiting advances in machine learning. Okay, and so the setup is that the name GameTime comes from the fact that we think of the platform as an adversary, and it's a game between the tool and the platform. So it's an area of machine learning known as game theoretic online learning. Okay, so that's a quick overview of GameTime, and you can do a lot of fun things with GameTime. You can even predict distributions of execution times and so forth. I want to end with some open problems here. This is really a very current research topic on which a lot needs to be done. Some of you, many of you would be aware of the problems that Toyota had recently, right? With all the recalls, they had this unintended acceleration problem. And so recently, NASA was commissioned to do a study of the reasons of why this problem happened. And they came up with a several hundred-page report. And one of the sections of that report is on the software. It's on the electronic system, the embedded system aspects. And it's actually pretty interesting reading. They say there's a lot of things that the state of the art in analysis tools is really weak. And they have a whole section on timing analysis where they talk about a lot of the problems that we talked about today with these kinds of tools. So some of the two of the main problems that are there today is that processors are getting more and more complex. So people are moving to multi-cores, but the analysis tools, as I said, they can't even deal with multi-threaded programs. They can't even deal with interrupts, right? So it's like it's actually scary. I was talking to some automobile companies, and some of the managers there, they want to move to multi-core, but they don't really know what the implications are of moving to multi-core, just in terms of the kinds of bugs that will show up in concurrent software and in real-time constraints. So I think that they are going to move to multi-core, and we have to be able to develop tools that will help them write correct programs for those platforms. So architectures are getting more complex. So the question is, can we create processor models, and even can we rethink how we do processor design to make timing analysis easier? So Professor Lees has a project called PRET, which is trying to do that. And then the second thing is, even assuming that architectures are going to get complex and we can't do anything about that, what can we do with the analysis techniques to make them more robust? And this is where GameTime fits in. And we're also doing things about extending it to deal with interrupts and so forth. Okay, and always there's a problem of measuring execution time, which has to be handled. Okay, so I think that's all I wanted to say. So chapter 15 has a very basic introduction to this issue, but if you're interested in this topic, come talk to me afterwards. Oh, there's a couple of announcements. So I have 2 announcements to make, and then I think Rafael has an announcement as well. So the first announcement is project presentations. Like I sent in my email yesterday, The presentations will be on May 11th, 11:30 to 2:30 p.m. Okay, that's the final exam slot for this class, so I assume it should work for everyone. But if not, just come and talk to me. And then the second announcement is, I believe last week when Professor Lee lectured, there was a guy from Tektronix who was attending. Turns out he has internships available. So if you're interested in an internship at Tektronix, then send email to Professor Lee. Okay? And Rafael?